Hello everyone. In this video, I'll solve 10 questions of linear algebra. Let us take up the first question. Suppose the matrix A equal to, this is the given matrix, has certain complex number lambda not equal to 0 as an eigenvalue. So one of the eigenvalue is given, that is lambda. Which of the following numbers must also be an eigenvalue of the given matrix A? Now look at the given matrix. Take row sum of each row. That is first row sum equal to 40 minus 29, 11, 11 minus 11, 0. Here also minus 18 minus 12 minus 30 plus 30 0. 26 plus 24 50 minus 50 0. So each row sum equal to 0. So we know that if each row sum equal to some constant, then that value is the eigenvalue, one of the eigenvalue of the given matrix. So 0 is an eigenvalue of the given matrix A. Now we have the formula trace of A equal to sum of eigenvalues of A. So we know two eigenvalues, one is lambda and one is 0. We want the third eigenvalue now. Lambda plus 0 plus mu equal to trace of A. Trace of A is sum of diagonal elements 40 plus 30 minus 50. So mu equal to this value is 20 minus lambda. Third option is the answer. Next, second question. The determinant of the matrix. This is the given matrix. We have a formula. If you have any matrix of the form alpha, main diagonal element alpha and the diagonal element beta, then its determinant is given by alpha square minus beta square to the power greatest integer of n by 2. So this value is nothing but greatest integer function. You can represent it like this also. Yeah. When here in this case n is even, so this is for any general formula. N is even because n equal to number of rows. Here there are 6 number of rows or column, that is the size of the matrix. So alpha equal to 1, beta equal to 2. Let me substitute in this formula. So we will get 1 square minus 2 square to the power n is 6, 6 by 2. Greatest integer of 6 by 2 is nothing but greatest integer of 3, as it is an integer, is equal to 3. So if you don't know how to define greatest integer function, then I had made a video on greatest integer function before. Please watch that video to know more about the greatest integer function. So it is 1 minus 4 whole cube. So this is minus 3 whole cube, which is minus 27. Third question, the determinant of the n by n permutation matrix. So this is the given matrix. Main diagonal, every other entry is 0. Only these diagonal elements are equal to 1. So you can apply the same formula as before. Alpha equal to 0 here, beta equal to 1, n is n itself. So make use of the formula 0 square minus 1 square equal to the power n by 2. So greatest integer of n by 2. So second option is the answer, minus 1 to the power n by 2. Fourth question, let A, B be n by n matrices such that they will satisfy this condition where I is the identity matrix. Which of the following is always true? Let us make use of the given result, that is BA plus B square equal to I minus BA square. So I'll bring it here. BA plus B square plus BA square equal to I. So B into, let me take B common, A plus B plus A square equal to I. So B into this whole matrix, when added up together, gives you another matrix. Let me name it as C. So BC equal to I. Product of any two matrices equal to I means one is the inverse of another. So B is invertible, therefore, because there exists some matrix which gives you BC equal to I. B is invertible. So if B is invertible means determinant of B is not equal to 0. Hence B must be a non-singular matrix. That is always true. Fifth question, the determinant of this, what is the value of the determinant? You have to find out. You have to apply a series of row operations. R2 changes to R2 minus R1, R3 changes to R3 minus R1. Do like this. 1 minus 1, 0, y minus x remains, then y minus x plus y square minus x square. Similarly, R3 minus R1, 1 minus 1, z minus x plus z square minus x square. Now look at the second row. In the second row, y minus x is common. Y minus x is there. Here this can be written as y plus x into y minus x. Here 0 into y minus x you can write, because 0 into anything it is 0. So y minus x is there in every term of the second row. So take it outside. Similarly, z minus x in the third row. So it remains, these values, these terms will remain. Now it is easy to calculate the determinant. Delete first row, first column. So you will get z plus x minus y minus x get cancelled. So the answer is the first option. So this is the answer, z minus y, z minus x, y minus x. Next question, let A be a 5 by 5 matrix with the real entries such that the sum of the entries in each row of A is 1. Then the sum of all the entries in A cube is, there is a formula. If sum of each row of A is lambda and A is an n by n matrix, then sum of entries in A power m is n into lambda power m. So it depends on the order of the matrix and the sum of each row, that is lambda. So it is lambda to the power m into n, order of the matrix. Here in this case, lambda equal to 1, then m equal to a cube, we have to find out 3, n equal to, it is of order 5. So substitute all these here, you'll get 5 into 1 cube, that is equal to 5. Sum of all entries in a cube is 5. Now, seventh question, let A equal to, this is the given matrix, where Aij is given by Bi square minus Bj square for some distinct real numbers, B1, B2, so on up to Bn. Then determinant of A is. Let me check for n greater than or equal to 3. This is how the matrix is defined. Let me check for n equal to 3. Take 3 distinct real numbers like B1 equal to 1, B2 equal to minus 1, B3 equal to 0. So from this Aii, you can easily calculate Bi square minus Bi square. So diagonal elements Aii, Bi square minus Bi square, that is always 0. So all the diagonals will be 0. Now remaining elements you have to find out. So this is nothing but A12, this element is A13 and so on. A12 is B1 square minus B2 square. So B1 square is 1 square minus 1 whole square, 1 minus 1, that is 0. Similarly, A13 is B1 square minus B3 square. B1 square is 1 minus B3 square, that is equal to 0. So this gives you 1. Similarly, rest of the entries you find out. Now look at the matrix. It is a skew symmetric matrix. Principal diagonal element 0 and the rest all negatives of each other. Like when you take the mirror image, 0, 0, 1, minus 1, 1, minus 1. So it is a skew symmetric matrix and it is of order 3, odd order. So you know that skew symmetric matrix of odd order always has determinant value equal to 0. So for 3 by 3 it is coming out to be 0. If it is true for that, for the rest all also no need to verify. There is an option called as 0. That is the answer. Eighth question, let J denote the matrix of order n by n with all entries 1 and let B be a 3n by 3n matrix given by B equal to, this is the matrix. Then rank of B is, so there are 4 options are given. Now let me check n equal to 1, take n equal to 1. Then J becomes, J denotes matrix of order 1 by 1. So it is a matrix containing only one element 1. Let us substitute that value here. That is a matrix with 1, matrix with the entry 1, matrix with 1, 3, 1. So you know that rank of B, look at the matrix. So first row, first column, there is a non-zero entry. So rank of B is equal to 3. So because you don't have any non-zero, zero rows, you have to count the number of non-zero rows. There are 3, hence rank of B equal to 3. Ninth question, let A equal to 1, minus 1, 1, then 1, 1, 1, 2, 3 alpha and B equal to this. Then the system Ax equal to B over the real numbers has 4 options given. You know that Ax equal to B has a unique solution if determinant of A not equal to 0. So this is the condition. If determinant of A is not equal to 0, then it will have a unique solution. So we have to check is determinant of A equal to 0 or not. So take the value of the matrix A. Take the matrix A, find its determinant. You can, instead of simplifying, evaluating the determinant, we can simplify it further using the row operations. Then 1 minus 1, 0, 1 minus of minus plus 2, and 1 minus 1, 0. Then 2 minus 2, R3 minus 2, R1. 3 plus 1, 3 plus 2, 5, alpha minus 2. When you evaluate using first row, first column, it gives you 2 into alpha minus 2. So now this determinant becomes 0 only if alpha equal to 2. Okay. Therefore, the fourth option you check, A has unique solution. A unique solution exists if alpha is not equal to 2. Because if determinant of A is not equal to 0, then it has a unique solution. Now determinant of A equal to 0 if alpha equal to 2. So unique solution if alpha is not equal to 2. Last question. Let A be a 3 by 3 matrix with real entries such that determinant of A is 6, the trace of A is 0, determinant of A plus I equal to 0, then eigenvalues of A are. So given determinant of A plus I equal to 0, so that is, I can reframe it as A minus of minus 1 into I equal to 0. So this is the characteristic equation of the matrix A. So in the place of lambda, you know that a determinant of A minus lambda I equal to 0 is the characteristic equation of the given matrix A. In the place of lambda, I have minus 1. So I got one of the the eigenvalue of the matrix A, that is minus 1. Let two other eigenvalues, because it is a 3 by 3 matrix, lambda 1, lambda 2, be the other two eigenvalues of A. Product of, again same formula, product of eigenvalues equal to minus 1, lambda 1 into lambda 2 is minus lambda 1, lambda 2. That is determinant of A. Determinant of A given it as 6, substitute here. Lambda 1 into lambda 2 is minus 6. Similarly, trace of A equal to minus 1 plus lambda 1 plus lambda 2 is equal to the sum of eigenvalues equal to trace of the given matrix. Trace of A is 0. Both had been given to you. So 0. So lambda 1 plus lambda 2 equal to 1. So make use of these two in this formula. Either you can go that way or else directly you can check with the options. Because one of the eigenvalue is minus 1. So the rest to two eigenvalues we want, which satisfies this condition. Lambda 1 into lambda 2 equal 2 into minus 3 gives you minus 6. And 2 plus minus 3 gives you this 2 plus minus this is not possible. So whereas the fourth option, minus 2 into 3 gives you minus 6. Minus 2 plus 3 gives you 1. Both are satisfied at that time. So fourth option is the answer.